Human-powered airplane project, and we're here to give a retrospective presentation. And I am Declan. I'm the project manager.
My name is Joseph Shea. I'm the chief engineer.
And my name is Jackie Thomas. I'm the previous project manager.
And today we'll go over the background of the human-powered airplanes in general. Afterwards, we'll go over the goals and requirements, then the design analysis, and afterwards, final design. Then we'll go through our current progress, and finally our budget and our schedule.
Alright. So a little bit about background. You may ask, what is a human-powered airplane? This has never been done before. Well, a human-powered airplane is an airplane whose flight power comes from the pedaling output of a pilot. Human-powered airplanes have existed as early as 1921, where we saw airplanes that were essentially wings strapped to bicycles. Amazingly, things like this were able to hop distances of roughly 12 yards, but since then airplanes have gotten bigger. In 1961, Southampton University created the SUMPAC HPA. You can see this on the second picture. This airplane was able to fly a total distance of roughly 650 yards, which was the longest distance at that time. And then the human-powered airplanes continued to grow in performance, and the performance of human-powered airplanes peaked roughly in 1988 with the Daedalus HPA shown on the third picture. The Daedalus HPA was able to fly for roughly 2.5 hours over the Sea of Crete, and that was a pretty big feat. Well, roughly around the same time, UC Irvine was actually creating human-powered airplanes as well. You can see this picture on the far right over here. That was the Big Bird HPA, which that particular one barely did not take off. However, a few UC Irvine HPAs did. However, after roughly around 1990, UC Irvine reached a hiatus in the human-powered airplane projects until roughly a few years ago. A couple of students at UCI wanted to do something different and wanted to do a big project that would be that would allow them to learn a lot about airplanes. It would also allow them to do a project that, for example, did not create pollution, was environmentally friendly, something that could be student-run yet was also very big, where the students were actually able to create an airplane that was full-scale life-size. Well, human-powered airplane was a good way to go. So that was basically the motivation for why this project was started. It's a very good project for a lot of ideas to be tried and tested. Things that are learned in the classroom can be applied to a very big project. So we created some goals for the human-powered airplane that has currently been designed within the past couple of years. Obviously, the first goal was to design and manufacture a human-powered airplane. To test fly that human-powered airplane, it was not meant to just be a showpiece, it's meant to actually fly. We are from there going to analyze results from the test flights to check the potential of a low wing cantilever wing configuration, which we will get into later. That was one of our goals for our particular plane. We were going to then use the test data to check our predictions, and finally to document our results to lay further groundwork for future HPA projects, hopefully here at UC Irvine or elsewhere. So now some further project requirements for our plane. Safety is a very big concern for human-powered airplanes, so pilot and ground crew safety is going to be a major concern. The design itself must be affordable, somewhere around the scope of $10,000 is about the max. It has to be easily constructible because we're all students building this airplane. It was not intended to be something that you'd have to outsource to an outside company. Flight power would have to be achievable by human. And finally, the project had to be lightweight.
Laser pointer?
Yeah. Wrong, other side. Click on the laser pointer's on the back of the mouse.
Okay.
And then
How do I go back?
the two tops.
Go back on that one, Jay.
Okay. So these are some of the design options that we considered for our human-powered airplane and for human-powered airplanes in general. These are sort of the configuration choices that you can make. One of the more important ones is if you want to use wire bracing or not. This is an example of a compromise of using only 2 wires to to support some of the lift loads from the wing, whereas some of them you'll see have wires going every which way. Now, the trade-off there is if you have a lot of wire bracing, then you can make the structure lighter, but it's considerably more draggy, especially if you're flying faster. Now, the next difference in configuration is you can either do a high wing, which the majority of HPAs have done in the past, or a low wing design. The trade-off here is with the low wing design, you need a cart beneath it in order to take off so the propeller doesn't hit the ground. Now for the tail, there is either a cruciform tail, this is a pretty popular choice, or our initial design we decided to go with an H-tail for ground clearance on rotation. And the spar can either be round or rectangular. The rectangular spar is more optimized for the lifting loads since most of them go in this direction as opposed to the drag.
A couple options we use to analyze our design or major programs. One of the most significant programs was a program we made ourselves, a spar designer. What it did was we inputted certain flight loads into the program, and then the program gave out the ideal carbon fiber layup schedule to make a carbon fiber wing spar, along with a prediction of how that spar would react to the flight loads. So what we did was we made a carbon fiber spar according to that layup schedule. We then tested it and broke it, and compared the data, the deflection data of the actual spar to the predicted data of the program. Then we recalibrated the program until the two matched, and we thus had a dependable program that could predict how our spar reacted.
Now, after we have the spar designed and the major structural components designed, we can have an estimate of how much it's going to weigh. So once we know how much the airframe is going to weigh and how much the pilot weighs, then we put that information into the spreadsheet, which we call the power plotter. So for this spreadsheet to work, we need to know the weight of the empty airplane as well as basic information about the geometry of the airplane so we can estimate the drag. So with that, then we can get important parameters such as the L over D, and so what the best speed to fly at would be, and also the power required to fly this airplane. That's really important for us to say, is this achievable as far as the power, and are we flying off design? Now after that, we also use the Athena Vortex Lattice, better known as AVL, which is a program that can estimate the stability and control derivatives of our airplane. So this is mostly to check to make sure there won't be any handling issues with the airplane, and to make sure that under the different flight conditions we're likely to encounter, it's recoverable. And this is a plot of the wake of the plane in the Trefix plane. So this is the initial design that Jackie and Joe came up with in the summer of 2013. It does not use any wire bracing at all, so that reduces the drag. It is a low wing configuration that potentially reduces the amount of frontal area on the fuselage. The spar is cantilever and a rectangular spar optimized for the bending loads due to lift. The tail is an H-tail, and this also allows us to use a short drivetrain between the pilot's feet, pedaling, and the propeller, which is potentially more efficient. And takeoff is via detachable launch prime. Now, we've gone through and looked at the design and constructed a lot of the parts. And after that, we've decided that there's some manufacturing challenges that make that design less feasible in practice than it is sort of on paper. So we've modified parts of the design, and our current design still uses the same wing with the fully cantilever spar. However, now it's been moved up top with the fuselage underneath. The main reason for that was this makes mounting the landing gear a lot easier. We can just put it here, we don't have to have a separate cart, and worrying about how to hold it on the cart and being able to detach from the cart on takeoff and clearing the cart, issues like that. So that's the high wing, and the drivetrain now is a bicycle chain that runs from the pedals down here up to the propeller. And the motivation behind that was so we can use more off-the-shelf components that are quicker to build as opposed to custom machining components for the bevel gear drivetrain.
And here are the current specifications for our current design. We have a 108-foot long wingspan, a 12-foot diameter propeller, And our current flight weight is about 300 pounds, which forces us to fly at 17 miles an hour and have our propeller spin at 200 RPM. And our current progress is that we have all of our wings completed and fully covered and skinned. Our tail booms are also fully manufactured, along with our tails, which can assemble into each other to make a tail boom and tail configuration. Our control surfaces are also all working right now. We can pull some control wires and be able to move all of them. All of our propellers are also manufactured. You can see me standing next to one of them on the left. And our propeller hub has also been machined. We were able to make it adjustable for pitch as well, and found a way to do that by taking a shaft and putting in holes at the angles we desired. And finally, our fuselage frame has also been built. And here's our budget. This is a bit outdated. A few days ago, we did a thorough breakdown of everything we needed to buy, so this current budget is a bit off. But originally, our drivetrain was our biggest cost because we had not fully made it yet, and we're running into issues about obtaining all the parts, which ballooned our drivetrain costs.
One of the things that's interesting about the cost projection was, for this one, we essentially went through and had each team lead give us a number for how much do you think you'll need to complete your part of the project. And then we tallied that up together to get this figure of almost $9,000. Now, a few days ago, we went through and did a different approach. Essentially, we tried to do a giant purchase order. So on a purchase order, it has how many do you need, what the item is, who the vendor is, and what the price. So we went through and did a list that had maybe a few dozen items that we actually needed to buy. And we found that the price actually got a bit cheaper than what we projected here. So I think that would be a useful tool for projects in the future, is to actually look up what everything costs to the best of your knowledge, if you can, if you're far enough along in your design.
And a schedule is to have the controls working by June 11th and calibrated by June 25th. Have the wing mount and the drivetrain installed by July 8th. Assemble the fuselage by the 22nd. And have construct a fairing by August 4th. And then our ultimate goal is to test fly by August 21st. And we've learned quite a few lessons over the past year. We learned about various different additional ways to manufacture aircraft airplanes. One of the most important that I personally discovered was how to attach all the leading edge caps onto the wing to turn from a skeleton into an actual wing. We also learned it's a necessity to communicate amongst the team leaders. Joseph and I had quite a few communication problems early in the year, which significantly hampered the project.
Yeah, one of the things that we learned about that is because we had different schedules. Dad came in earlier during the day, and I tended to come in the afternoon and stay through the night. It was really important for us to have a few hours of time where we can just meet face to face and sort of think about, oh, this is something I want to talk to them about. And if they're not there, call them right away. I think it's really important to just have everyone on the same page and just get to know the person that you're working with somewhat better on a personal level rather than just sort of professionally.
Yeah, and another issue we ran into was we didn't check our assumptions. The biggest example of this was attaching wing skin onto the wings. The leaders before us, Jackie and Joe, assumed it would be extremely easy and almost trivial to attach wing skin. When I actually tried to do it, we found it was significantly harder than we ever hoped or thought, because none of the parts were manufactured perfectly. We had run a bunch of tolerancing issues, and nothing fits correctly. So we spent a good almost 2 quarters trying to figure out how to attach all this wing skin together, when they should have taken us, much shorter according to our initial time frame.
Yeah, little details like what sort of glue to use, what sort of tape, and what actually sticks to what was quite challenging to figure out.
And we also found out that time and money were both very important commodities, as important as, if not more important than a good design. Because while we had the design, we didn't have enough money to invest in resources to train our members or to procure resources in general at first. And so we had a whole bunch of inexperienced members who really could not get any kind of experience because there were insufficient materials at first.
Yeah, so what we found is the design really should be driven by how much money and how much time you have. Because if you have something very complicated, like I think you guys found out about that, is If it's complicated, then you run into sort of the time issue further down the road. Or if it's complicated, it could potentially cost more. So we're having that issue now and trying to see how we can simplify the design to meet the time and the money constraints.
And probably the biggest lesson I learned was for a multi-year project like this, it's very important to be able to retain members over the years. What happened last year was only a handful of people were retained on a project that continued from last year. So that none of the designs were reset, so there were a lot of decisions that were made that no one really knew why they were made. And so it took an extremely long time getting everyone up to speed. And that's all we have. And do you guys have any questions? Yeah.
So how many